Hi, Flipping.
Hmm?
Go back there again to more.
More?
Say hide floating reading controls.
Oh, that's good. And escape brings him back?
Yep.
All right. Well, I learned something today. Okay. So we're going to talk about circuit components, semiconductor materials, and then diodes and digital ICs. Uh, maybe get that far today. Next week, we'll pick up with where we didn't get to and toroids and solenoids and analog integrated circuits and electro optics, uh, optical encoders and optical isolators, things like that. So in this one, we'll talk about semiconductor materials and how semiconductors actually work, how they're made. There's two basic materials that are used, germanium and silicon, primarily silicon today. There's still some things, some diodes, and a few other things made out of germanium because of the low uh, junction voltage. But most things are based on silicon. And we have two types, a P type and an N type. In the P type, it's a piece of silicon, and we call basic silicon intrinsic silicon with an I, which will show up later when we talk about a pin diode. A P-type silicon has impurities embedded in it when they grow the crystal. And in the case of a P-type, they use something like boron, where um, it only has 3 valence electrons and silicon has 4. So when you put it in the crystal matrix, you wind up with a hole. So it has a positive charge. In the N type, you put something like phosphorus in it, and it has 5 valence electrons. So you wind up with an extra electron. So it's negative. And that's where the P and the N come. And also, when we get into the transistor types, they're both NPN and PNP with the bipolar junction transistors. And then in the field effect, uh, you have what's called enhancement mode and depletion mode types. We don't do a lot on those, but there's some questions on it. So, uh, and then the metallic oxide semiconductor or complementary metallic oxide semiconductor. The integrated circuits, the digital circuits tend to be made either with transistor logic, which is bipolar transistors, or complementary MOS. There are lower power versions, uh, not quite as high a frequency, but they use a lot less power, a little better noise immunity. And then also in the case of field effect, you can have an N channel or a P channel, just like you can have an NPN or PN junction transistor. So like I said, most of the stuff today is made from silicon. There's some things still from germanium. You'll see gallium arsenide and gallium nitride for some very high frequency stuff. Uh, Silicon itself is called a semi-metal, where it falls in between the metal category and the periodic table and the non-metal. And it's because it has 4 valence electrons. Metals will have 1 or 2. Non-conductors will have 7 or 8. You can only have 8 in that outer valence shell. Here's the unless they've found some new ones. Here's the current periodic table. And you can see these blue are in the semi-metal category. So silicon is one of them. Boron happens to be in there, as well as arsenic. That's also something they use for doping the silicon, and antimony. The metals themselves are over here in the yellow. That's where your copper and silver and gold and aluminum's in there somewhere. So I mentioned, does everybody know about atomic structure of an atom? The Bohr model, where you have these shells, you got a nucleus, which is protons and neutrons, and you have an equal number of electrons circulating around, uh, equal to the number of protons. And they have different energy levels, which they called shells in the Bohr model. When you get to the Heisenberg model, they talk about electron cloud and the probability that are in different energy states. So we're not going to talk about that one because it's too confusing. The outer shell of that electron or atom, we call the valence shell. I'm not exactly sure what valence means, but in the chemical world, that's how they can make bonds between atoms. And you can have electrons in that outer valence shell actually have kind of half in one atom and half in another atom. We call that a covalent bond. So if you have two silicon atoms, they will both share those outer electrons. It's like they're bound together, and those electrons are in one or the other. And in conductors, where I talked about, they only have one or two valence electrons. The energy level for that outer valence shell is essentially equal to what we call the conduction band. And that's an energy level where the electrons, when we call it a free electron, it's been energized enough to leave the atom, and it's in the conduction band where it can go find a hole with another atom that's missing an electron, and it gives off that excess energy when it falls back into the other electron, because it had to have additional energy to escape the atom. And the amount of that energy will come up later. That's the energy that's actually being dissipated or carried from one atom to another. And we think of that charge as moving, where it can appear to move at the speed of light, where the electrons don't really move like you might have been told. Electrons actually move at 0.01 millimeters per second. That's not very fast. But the charge can effectively move from atom to atom at the speed, almost the speed of light. So when it's a conductor, you can have electrons that are with a slight amount of energy, even thermal, can be free to go bond with other atoms that are missing an electron and move that charge along with them. In the case of a semiconductor, there's a large, what we call a band gap. So the energy required to move that electron out of the atom up to the conduction band where it can move around, and this one is showing it's about 1 electron volt. It turns out in the case of silicon, that represents about a 0.6 to 0.7 volt potential in order to cause that to happen. And you're going to see that when we talk about diodes and transistors. There's that junction bias voltage, which is a result of that. When you have something like an insulator, where you got 7 or 8 electrons, the band gap is very, very wide. So it takes a tremendous amount of energy. In this case, they're showing 5 electron volts. So it's 5 times in order to get an electron mobile, which is why they don't, insulators don't conduct until you apply enough potential or energy in order to free those electrons. And usually it results in fire and smoke and things. This is just showing, kind of a Bohr model and that outer shell for silicon where you've got 4 electrons circulating around, which we call the valence electrons. And showing, because silicon is this nice with 4 electrons that can mate with one another, it makes a nice crystal. So by nature, it is a crystalline structure. And like I said, you can add impurities, we call doping, to that silicon to make it either an N-type or a P-type material. And if it's an N-type, which has excess electrons, free electrons in it, we say the majority charge carriers are the electrons. In the case of a P-type, where we're missing an electron, the majority carrier is a hole. And sometimes we call that an acceptor. And in the N-type, it's a donor. So which of the following semiconductor materials contain excess free electrons? Good.
Because electrons will bring you negative.
They have a negative charge because Benjamin Franklin said so.
It says
And it was totally arbitrary. They didn't know. That's why positive flows to negative, because they didn't understand charge and electrons. It turns out they're both wrong because it's really other things that move, because the electrons don't really move very far. These impurity atoms can add holes, okay? So that's an acceptor for an electron. And if I go the other way to make an N-type, then I have free electrons in that crystal structure because I have atoms in there with 5 connected to atoms with only 4. So there's one that can't do a covalent bond. This is just a picture showing if I use phosphorus to make an N-type because it's got 5, and boron to make a P-type. So we wind up with a hole over here or a missing electron. What is the name given to an impurity atom that adds holes to a semiconductor crystal structure? So we're going to add a hole. An acceptor. Sometimes we use gallium arsenide or gallium nitride. They operate better at higher frequencies, and they also have a lower junction or band gap. In what application is gallium arsenide used as a semiconductor material? Microwave. Okay. If we take these two together and put them together, the P-type and N-type silicon, we have a junction. So we have holes on one side and electrons on the other side. So, but what happens is the free electrons on the inside kind of migrate and fill in the holes on the p side and create what's called a depletion zone, because in that area where they've recombined, it's basically back to intrinsic silicon. So it doesn't have a positive or negative charge. So that has to be overcome in order for current to flow through that p-n junction. When we apply a voltage, a bias voltage to the p side of the junction and a negative to the n side, you get an electric field formed across that because it's got charge positive on one side, negative on the other, and that depletion zone in the middle, which is looking like a dielectric. And when you get up to the bias voltage, in the case of silicon, it's 0.6 to 0.7 volts, it will start to conduct current from the positive to the negative. If I apply it in reverse and I put a negative voltage potential on the P side, then it's going to increase the size of the depletion region. Now, one of the things that turns out is they make use of that fact to create varactor diodes, because reverse biasing a diode, you can change the capacitance of it. So that becomes a way to make a electrically variable capacitor. But all diodes have that effect. The capacitance in that junction will change depending on the reverse bias. And that electric field that's formed between the positive and the negative across that junction is that bias or junction voltage that we have to overcome for it to conduct. This is a little thing showing where the junction is. This yellow area is really the depletion zone, and the potential across that is this, in the case of germanium, it's about 0.3 volts. In the case of silicon, it's as much as 0.7. I think the gallium arsenides are down there in the 2 or 3 tenths of a volt range. So it will conduct from positive to negative. It will not conduct negative to positive, although there's some slight leakage in the real world. And this is kind of what I just said. Basically, that it's not supposed to conduct in the reverse biased direction. It's supposed to conduct after you exceed the junction voltage. So why does the PN junction diode not conduct current when reverse biased?
I remember you saying, well, I need the depletion region, so I'm gonna guess C.
You paid attention.
I'm listening.
I think that's the right answer.
That's good.
Okay, so we talked about a diode. It's just a simple PN junction. So now we're going to have 2 PN junctions. We're going to take a piece of N, some P, and another piece of N, and make a sandwich. This is a kind of a cross section of how a typical bipolar transistor is formed. And they actually can, they don't physically bond these together, they grow them like this. I don't know what the process actually is. And we label these 3 areas where we make some contact with it with some sort of metal plating or a wire as the emitter, the base, and the collector. In the case of the bipolar, the collector is the largest amount of material. We're showing here an NPN. This could also be a PNP, and they work just the opposite. And what happens in this one, if I apply a voltage to the base relative to the emitter, it looks like a diode. I have a PN junction, it works the same way. It can conduct when I exceed the bias voltage from the base to the emitter. Now, because of the positive field over here on the collector, I don't know that I can explain it, but there's kind of an avalanche effect, which also causes current to flow from the collector to the emitter through this NPN region. And it has to, again, to do with another depletion zone on that other junction, which I don't know that we need to get into. This is kind of showing the effect where we're injecting holes, which are effectively moving from the base to the emitter, from the P to the N, and this is an NPN. There's some holes that are actually recombining in this depletion area, and then we're getting electrons to flow across the junction from the emitter to the collector, which means holes are moving from the collector to the emitter, because that's our conventional current flow where it flows positive to negative. And it takes 0.6 to 0.7 volts for that to start happening. The standard symbols for an NPN and a PNP transistor are drawn like this on a schematic. So when you forward bias a silicon NPN junction transistor, you get a small base current flowing and a much larger collector to emitter current. And that's called amplification, because a small amount of control current on the base can cause a much larger change in collector to emitter current. We call that the gain or the beta of that transistor. And it's really defined as the ratio of the collector current per base current. So how much the base current affects the collector current. And that's how we get amplification out of it. It turns out that if you go back to this one, it turns out that the thickness, the physical thickness of this base layer is what affects the amplification of the beta. So the thinner that is, the higher the gain. The downside is the thinner it is, the lower the voltage it can operate at, because you'd have a breakdown voltage. So again, you don't get something for nothing. So you don't get as much gain on high power devices as you do on low signal devices. So which of the following indicates that a silicon NPN junction transistor is biased on?
That's the 6 to 7 volts you're talking. So B.
So which one is it?
B. I mean, 0.6, sorry, 0.6, 0.7, so D, yeah.
So the answer is?
D is delta.
Delta. Base emitter of 0.6 to 0.7 volts. And it varies. That's why it's a range. Depends on the actual structure. What is the beta of a bipolar junction transistor?
So. The ratio.
Right. Change the collector current with respect to the base current, or the ratio of the two. We have another one on this, which I looked through a lot of data sheets for transistors, and hardly any of them actually specified the alpha, but it's on the exam. So we'll talk about it. And if you configure a bipolar transistor in what we call a grounded base circuit and apply a 1 kilohertz signal, the frequency, or excuse me, yeah, you do it relative to one. As you change the frequency, when it gets to the point where the output of that stage is down to the half power point, or 0.707 of the input voltage, we call that the alpha cutoff. So you baseline what it is at 1 kilohertz, and then you do the frequency plot and see where it's down to 0.707 of what it was at 1 kilohertz. And that defines the alpha cutoff frequency. In other words, the highest frequency that you'd be able to use that transistor in a circuit, in a practical circuit. I don't know how much it's used. Like I said, I couldn't find it defined on most transistor data sheets. They'll give you beta and all sorts of other things. What is the term for the frequency at which the grounded base current gain of a bipolar junction transistor has decreased to 0.7, actually 0.707, of the gain obtainable at 1 kilohertz? And there's only one question on that. All right. Field effect transistors are different. A bipolar junction transistor is a current device. So the current in the base emitter determines the current flow from collector to emitter. So it's proportional based on the beta of the transistor. In a field effect, it's more like a vacuum tube, where it's a voltage controlled device. So the voltage on the gate controls the amount of current flow between the drain and source. And in case of emitter, base, and collector, we call them gate, drain, and source, where the gate is the controlling element. The source is the lead that is supplied electrons, so it would be the negative. And the drain is where the electrons come out and go back to fill in with holes, because these were developed after they kind of discovered holes as and electrons moving. So they named them drain and source. It turns out that most of the field effect transistors, the way they're manufactured, they're symmetrical. So at least for the simpler ones, it doesn't matter which one you use as drain and source. As long as the voltage, the controlling voltage is between the gate and one of them, it will control the current flow between the drain and source. We'll only talk about two types. The P-channel junction, which is represented by the figure 1, and the N-channel dual gate MOSFET, which is a metallic oxide semiconductor field effect transistor. And that's number 4 over here. So And then sometimes they do have a dual gate. Most of the time, it's a single gate MOSFET that you'll see in practice. So in figure 6.1, what's the schematic symbol for an N-channel dual gate MOSFET? B, number 4. In 6.1, what's the schematic for a P-channel junction FET? Okay. MOSFETs are slightly different than a junction FET. Junction actually has p-n junctions. In the case of a MOSFET, the gate is separated from the other parts of the silicon with a metallic oxide, which is actually an insulator. So it creates an electrical field, and that's how it controls the current flow, by that electric field either pinching off the flow because of another one of these depletion zones where it can widen it or deplete it. So that's how the voltage in that electric field controls the current from drain to source. Because these tend to be very high impedance input devices, they're very sensitive to electrostatic discharge. And in some cases, they may have Zener diodes in the package itself to protect them if you get a static charge on
Built
it.
into the MOSFET.
Hmm?
Built right into the MOSFET.
Right. Like this. And you don't always see them all over the place, but usually they'll have, and I think I've normally seen these back to back. So it can protect in either direction because you can use it either way. Everybody know what a Zener diode is? Because we haven't talked about it, but we're going to talk about it. Which seems like it should have come before transistors. How does DC input impedance at the gate of a field effect transistor compare with that of a bipolar transistor? See, it's on your tongue. Charlie. High input impedance. Bipolar has a low input impedance. It's a current device. What's the purpose of connecting Zener diodes between a MOSFET gate and its source or drain? Static protection. Okay. A FET can be an enhancement mode or a depletion mode device. If it's, and I always have trouble keeping these straight. If it's an enhancement mode FET, you have to apply a potential on the gate relative to the source or drain to cause current to flow. Because by nature, it has a wide depletion zone. And when you apply that bias voltage, you're decreasing the depletion zone, so more current can flow. A depletion mode device starts off with a narrow depletion zone, and it will conduct current without any bias on the gate. And you have to apply a negative bias on the gate to reduce the amount of current flow. It's very different than what you see with a bipolar transistor. In fact, the depletion mode works more like a vacuum tube triode. And this is just kind of showing the difference, the way they're made, where in the enhancement mode, you don't have this extra P channel in here. And on the depletion mode, you do. So that's why it can conduct without a bias. So what is a depletion mode field effect transistor? Okay. I didn't write any takeaways. I was tired. Where's, oh. I gotta bring it back.